All right, good morning. We're going to go ahead and get started. Homework 1 is due today unless you're using late days, and homework 2 will be released today. Homework 2 is going to be over function approximation and reinforcement learning. We're going to start to cover that material today, and then we'll continue next week with deep learning. The deep learning is not a prerequisite for this class, and so we're going to be releasing a tutorial on TensorFlow later this week. And then next week we'll also in sessions have the opportunity to go into some more of the background of deep learning. You're not expected to be an expert at it, but you need to know enough of it in order to do the homeworks and do the function approximation. We will be assuming that you're very familiar with things like gradient descent and taking derivatives and things like that. TensorFlow and other packages can do that automatically for you, but you should be familiar with the general process that happens. Before we continue, does anybody have any logistic questions? All right, let's go ahead and get started. As you can see, I have lost my voice a little bit. It's coming back, but we'll see how we go. And if it gets too tricky, then we'll take over. All right, so what we've been talking about so far is thinking about learning to be able to evaluate policies in sequential decision-making cases and being able to make decisions. All of this is when the world is unknown. And what I mean by that is that we're not given in advance a dynamics model or a reward model. And what we're going to start to talk about today is value function approximation. Just so I know, actually, who of you have seen this before? Who's seen some form of like value function approximation? Okay, so a couple people, but most people know. So when I say value function approximation, what I mean is that so far we've been thinking about domains where we tend to have a finite set of states and actions, and where it is computationally and memory feasible to just write down a table to keep track of what the value is of states or the value of state action pairs, or that we could imagine writing down a table to write down the models explicitly of the reward model and the dynamics model. But many real-world problems have enormous state and action spaces. So if you think about things like the Atari games, which we can debate about whether or not that's a real-world problem, but it's certainly a challenging problem. The state space we discussed at the beginning is really sort of the set of pixels. And so that's going to be an enormous space, and we're not going to be able to write down that as a table. And so in these cases, we're going to have to go beyond sort of this tabular representation and really think about this issue of generalization. So we're going to need to be able to say, we want to be able to make decisions and learn to make good decisions. And we're going to need to be able to generalize from our prior experience so that even if we end up in a state action pair that we've never seen exactly before, it's like a slightly different set of pixels than we've ever seen before, that we're still going to be able to make good decisions. And that's going to require generalization. So what we're going to talk about today is sort of starting with value function approximation for prediction, and then talk about control. And the key idea that we're going to start to talk about in this case is that we're going to be representing the state action value function with a parameterized function. So we can think of now as having a function where we input a state, and instead of looking up in a table to see what its value is, instead we're going to have some parameters here. So this could be a deep neural network. This could be, a polynomial. It could be all sorts of different function approximations, but the key here is that we have some parameters that allow us to say for any input state, what is the value? And just like we saw before, we're going to both sort of go back and forth between thinking of there being a state value function and a state action value function. And the key thing now is that we have these parameters. And we're mostly going to be talking about those parameters in terms of W. So you can generally think of W as just a vector, where that vector could be the parameters of a deep neural network, or it could be something much simpler. So again, why do we want to do this, and sort of what are the forms of approximations we might start to think about? So we just don't want to have explicitly store or learn for every individual state action pair. So we don't have to do that in terms of learning a dynamics model. We don't have to do that in terms of a value function or state action value function, or even in terms of a policy. We're going to need to be able to generalize so that we can figure out that our agents or our algorithms can figure out good policies for sort of these enormous state spaces and action spaces. And so we need these compact representations. So once we do this, we're going to get multiple different benefits, though we're also going to incur potential problems as well. So we're going to reduce the memory that we need to store all of these things. We're going to reduce the computation needed, and we might be able to reduce the experience. And so what I mean by that there is how much data does our agent need to collect in order to learn to make good decisions? So this is really a notion of sort of how much data is needed. Now, I just want to highlight here that there can be really bad approximations, and those can be great in terms of not needing a lot of data and not needing a lot of computation and not needing a lot of memory, but they may just not allow you to represent very good policies. So these choices of representation are defining sort of hypothesis classes. They're defining spaces over which you can represent policies and value functions. And so there's going to be sort of a bias variance trade-off here, and a function approximation trade-off, in the sense that if you have a very small representation, you're not going to need very much data to learn to fit it, but then it's also not going to have very good capacity in terms of representing complicated value functions or policies. So as a simple example, we could assume that our agent is always in the same state all the time. All video game frames are always identical. And that's a really compressed representation. We only have one state, but it's not going to allow us to learn to make different decisions in different parts of the game. So it's not going to allow us to achieve high reward. So there's going to generally be a trade-off between the capacity of the representation we choose, so sort of the representational capacity, versus all these other things we would like, versus memory, computation, and data. Now, there isn't always. Sometimes one gets lucky and you can choose something that's very, very compact and is still sufficient to represent the properties you need to represent in order to make good decisions. But it's just worth thinking that often there's this explicit trade-off, and we often don't know in advance what is a sufficient representational capacity in order to achieve high reward. Yeah?
Is this more or less... Is this more or less an orthogonal consideration from the bias variance trade-off in a functional approximation?
Yeah, you can think of it as Ben's question is whether this is an orthogonal trade-off to sort of bias variance trade-off. You can think of it as related. If you choose a really restricted representational capacity, you're going to have a bias forever, because you're just not going to be able to represent the true function. And then you'll have considered a smaller variance for a long time because it's a smaller representation. So it's related to that. If you've taken machine learning and talked about things like structural risk minimization and thinking about how you choose your model class capacity versus how much data you have in terms of minimizing your test set error, similar to that too. So, how do you trade off in terms of capacity to generalize versus the expressive power? All right, so a natural immediate question that I've started alluding to already is, what function approximation are we going to use? There's a huge number of choices. Today we're only going to start to talk about one particular set, but there's an enormous number, and probably most of the ones you can think of have been tried with reinforcement learning. So pretty much anything that you could do in supervised learning, you could also try as a function approximator for your value function. Could be neural networks or deep decision trees or nearest neighbors, wavelet bases, lots of different things. What we're going to do in this class is mostly focus on things that are differentiable. These are nice for a number of reasons, but they tend to have really nice smooth optimization properties, so they're easier to optimize for. So that's one of the reasons we're going to focus on them in this class. Those are not always the right choice. Can anybody give me an example of where, for those of you that are familiar with decision trees, where you might want a decision tree to represent either your value function or your policy? Yeah.
They tend to be highly interpretable if you keep them simple and you don't use an ensemble of trees, right? So in the case where you need to explain it to stakeholders or they need to actually understand, that could be helpful.
Exactly. So what's just said is that, depending on how you're using this sort of reinforcement learning policy, this may be interacting directly with people. So let's say this is going to be used as a decision support for doctors. In those cases, having a deep neural network may not be very effective in terms of justifying why you want a particular treatment for a patient. But if you use a decision tree, those tend to be highly interpretable. well, depending on which features you use, but often it's pretty highly interpretable. And so that can be really helpful. So thinking about what function approximation you use often depends on how you're going to use it later on. There's also been some really exciting work recently on sort of explainable deep neural networks, where you can fit a deep neural network and then you can fit a sort of a simpler function approximator on top. So you could fit first fit your deep neural network and then try to fit a decision tree to it. So you try to get kind of the best of both worlds, super expressive function approximator, and then still get the interpretability later. But it's worth thinking about sort of the application that you're looking at, because different ones will be more appropriate in different cases. So, probably the two most popular classes these days and in RL in general are linear value function approximation and deep neural networks. And we're going to start with linear value function approximation for two reasons. One is that it's been sort of probably the most well-studied function approximator in reinforcement learning, but up to the last few years. And second is because you can think of deep neural networks as computing some really complicated set of features that you're then doing linear function approximation over, at least in a number of cases. So it sort of provides a nice foundation for the next part anyway. All right, so we're going to do a really quick review of gradient descent because we're going to be using it a ton over the next few days. So let's just think about any sort of general function j, which is a differentiable function of a parameter vector w. So we have some vector w. It's going to be a set of linear weights soon. And our goal is to find the parameter w that minimizes our objective function. I haven't told you what the objective function is, but we'll define it shortly. So the gradient of j of w is, we're going to denote that delta j of w, and that's just us taking the derivative of it with respect to each of the parameters inside of the vector. And so that would be the gradient. And so a gradient descent way of trying to optimize for a function j of w would be to compute the derivative or the gradient of it, and then to move your parameter vector in the direction of the gradient. So if your weights, and generally we're going to always assume the weights are a vector, are going to be equal to your previous value of the weights minus some learning rate of the derivative of your objective function. So we're figuring out the derivative of our function, and then we're going to take a step size in that and move our parameter weights over a little bit, and then we're going to keep going. So if we do this enough times, are we guaranteed to find a local optima? Right. So assuming, so there may be some conditions on the learning rate, but yes, if we do this enough, we're guaranteed to get to a local optima. Now, notice this is local. So when we start thinking about this in terms of the policy, in terms of doing RL, it's important to think about where are we going to converge to and if we're going to converge. And I'll talk more about that throughout class. So this is going to be sort of a local way for us to try to smoothly start changing our parameter representation of the value function in order to try to get to a better approximation of it. All right. So let's think about how this would apply if we're trying to do policy evaluation. So again, policy evaluation is someone's given you a policy, they've given you a mapping of for a state what your action is, and it could be stochastic. So it could be a mapping from states to a probability distribution over actions. But someone's given you a policy, and what you want to do is figure out what's the value of that policy. What's the expected discounted sum of rewards you get by following that policy? So let's assume for a second that we could query a particular state, and then an oracle would just give us the value, the true value of the policy. So I ask you, what's the expected discounted sum of returns for starting in this part of the room and trying to navigate towards the door under some policy, and it says, okay, the expected discounted number of steps it would take you is on average 30, for example. So that would be a way that the oracle could return these pairs, and so you'd get sort of this pair of S v pi of S. And then let's say given that we have all this data, what we want to do is we want to fit a function. We want to fit our parameterized function to represent all that data accurately. So we want to find the best representation in our space of the state value pairs. So if we frame this in the context of stochastic gradient descent, what we're going to want to do is just directly try to minimize our loss between the value that we're predicting and the true value. So right now, imagine someone's giving us these true S value pairs, and then we just want to fit a function approximator to fit that data. So it's really very similar to just doing sort of supervised learning. And in general, we're going to use the mean squared loss, and we'll return to that later. So the mean squared loss in this case is that we're just going to compare the true value to our approximate value. And our approximate value here is parameterized by our vector of parameters. And we're just going to do gradient descent. So we're going to compute the derivative of our objective function. And when we do compute the derivative of that, then we're going to take a step size. And we're going to do stochastic gradient descent here, which means we're just going to sample the gradient. So what I mean by that is that if we take the derivative of our objective function, what we would get is we'd get something that looks like this. And what we're going to do is we're going to take, I'm going to use this as shorthand for updating the weights. We're going to take a small step size in the direction of this as evaluated for one single point. So now there's no expectation, and this is just for a single point. So this is stochastic gradient descent, where we're not trying to compute the average of this gradient. We're trying to just sample this gradient, evaluate it at particular states. And what I've told you right now is that someone's given us these pairs of states in the true value function. So you just take one of those pairs, compute the gradient at that point, and then update your weight function, and do that many, many times. And the nice thing is that the expected stochastic gradient descent is the same as the full gradient update. So this has nice properties in terms of converging. Yes, and name first, please.
So just to confirm, why is the expectation over a policy and not over a set of states if you were saying that for SGD it's a single state?
So this is over the distribution of states that you'd encounter under this policy. The question was, why do it over, what does the expectation mean in this case? In this case, it's the expected distribution of states and values you'd get under this policy. And it's an important point. Will come up later. It'll come up again later in terms of sort of what is the distribution of data that you're going to encounter under a policy. Of course, in reality, we don't actually have access to an oracle to tell us the true value function for any state. If we did, we would already know the true value function and we wouldn't need to do anything else. So what we're going to do now is talk about how do we do model-free function approximation in order to do prediction evaluation without a model. Okay, so if we go back to what we talked about before, we thought about either these sort of Monte Carlo style methods or these TD learning style methods where we could adaptively learn online a value function to represent the value of following a particular policy. And we did this using data. And we're going to do exactly the same thing now, except for we're going to have to, whenever we're doing this sort of update step of updating our estimator with new data, we're also going to have to do function approximation. So instead of just like incrementally updating our table entry about the value of a state, now we also have to reapproximate our function whenever we get new data. All right, so when we start doing this, we're going to have to choose a feature vector to represent the state. Let me just ground out what this might mean. So let's imagine that we're thinking about a robot, and a robot that, well, robots can have tons of really amazing sensors, but let's imagine that it's old school and it just has a laser rangefinder. A lot of laser rangefinders used to basically be 180 degrees, and so you would get distance to the first obstacle that you hit along all of this 180 degrees. So maybe here it's like 2 feet, and this is 1.5 feet, this is 7 feet, and it sort of gives you an approximation of what the wall looks like, for example. So here's our robot. It's got a sensor on it, which is a laser rangefinder, and it's telling us the distance to all of the walls. And so what would this feature representation be in this case? It would just be simply for each of these 180 degrees, what's the distance at 1 degree, 2 degree. That would be an example of a feature representation. Now, why, that sounds like a pretty good, maybe slightly primitive, but generally a pretty good feature representation. But what's the problem with that? Well, probably isn't Markov. So a lot of buildings have hallways that would say, on my left and my right, there's a wall about 2 feet away. And then there's nothing in front of me, at least for perhaps out to my laser rangefinder. It would just say, out of range. And that would be true for many different parts of the same hallway, and it would be true for many different hallways. And so there'd be a lot of partial aliasing. So this is a feature representation that probably is not Markov, but it might be reasonable. It might be a reasonable one on which to condition decisions. Maybe if you're in the middle of a hallway and that's what it looks like, you always just want to go forward. And that's an example of a type of feature representation, and again, just emphasizes the point that the choice of the feature representation will end up being really important. And for those of you who have taken sort of deep learning classes, you've probably already heard this, but it's kind of before deep learning, there was often a huge amount of work, there still is a huge amount of work on doing feature engineering to figure out what's the right way to write down your state space so that you could make predictions or make decisions. And one of the nice things about deep neural networks is that it kind of pushes back that feature selection problem so that you can use really high dimensional sensor input and then do less amount of hand tuning. So what do I mean by hand tuning? Well, in this case, you could use the raw features about like how far you are to on each of these 180 degrees, or you could imagine having higher level abstract features like trying to understand if there are corners. So you could already have done some pre-processing on this raw data to figure out what features you think might be relevant if you're going to make decisions. And the problem with doing that is that, again, if you pick the wrong set, you might not be able to make the decisions you want. Yes, and name first, please.
Could you please elaborate why this is not Markov, just kind of getting the 180 degrees of...
Yeah, so the question is, can I elaborate why this is not Markov? If you just have 180 degrees for a robot, if you think about something, say like a long hallway, let's say this is floor 1, this is floor 2. Like in gates, for example. So if you have your little robot that's walking along and it's guiding its laser rangefinder, it's trying to tell it the distance to all of the things, you're not going to be able to distinguish with that representation whether you're on floor 1 or floor 2, because your immediate sensor readings are going to look identical. And in fact, you're not even going to be able to tell where you are on that hallway for most of the hallway. Yeah.
So can we generalize that if we have partial aliasing, then we say it's not Markov?
Great question. Can we generalize and say if we have partial aliasing, it's not Markov? Yes. I mean, you could change the state representation to be Markov by including the history. And so then each individual observation would be aliased, but the whole state representation would not be. But in general, yes, if you have a state representation for which there is aliasing, it's not Markov. Might still be that you can still do pretty well with that representation, or you might not, but it's just good to be aware of in terms of the techniques one is applying. Okay, good questions. All right, so let's think about doing this with linear value function approximation. So what do I mean by linear value function approximation? It means that we're simply going to have a set of weights, and we're going to dot product this with a set of features. So, maybe it's my 180 degree sensor readings, and then I'm just going to have a weight for each of those 180 features. And we can either use that to represent a value function, or you can do that for a state action value function. Those of you who are already thinking about state action value functions might notice that there's at least 2 ways to do that once you start getting into Q. Just mentioned that briefly. You could either have a separate weight vector for each action, or you could put the action as sort of an additional feature, essentially. So there's multiple different choices. You get different forms of sharing. Okay. But for right now, we're just thinking about estimating the value of a particular policy. So we're just going to think about values, and we're going to say that, so remember, W is a vector and X is a vector now. X of S is just going to give us the features of that state. So it could be like the real state of the world is where the robot is, and the features you get out are those 180 readings. So we're again going to focus on mean squared error. So our objective function is this mean squared error, the difference between the values we're predicting and the true values. And this is our weight update, which is we want to update our weight by a learning rate times the derivative of this function. So what does this look like in the case of linear value function approximation? So what we're going to do is we're just going to take the derivative of j using the fact that we know that this is actually x times w. Okay. So what we're going to get in this case is delta w is equal to 1/2 alpha to v pi of s minus v hat of s w times x. Because the derivative of x times w with respect to w is x. Yes?
Is this expected value over all states or for a particular state?
Great question. Remind me your name one more time. Yes. So this question is this an expected value over all states or a particular state? When we're doing the update of the w, we're going to be evaluating this at one state. So we're going to do this for each state. We're going to see different algorithms for it, but generally we're going to be doing stochastic gradient descent, so we're going to be doing this at each state. The expected value here you can think about is really over the state distribution sampled from this policy. So if you were to execute this policy in your real MDP, you would encounter some states. And if you, and we'll talk shortly more about like what that distribution looks like, but we want to minimize our error over the state distribution we would encounter under that policy. Good questions. Okay, so if we look at this form, what does this look like? It looks like we have a step size, which we've seen before with TD learning, and then we have a prediction error, which is the difference between the value function, the true value function, and the value function we're predicting under our estimator, and then we have a feature value. So that's one of the nice aspects of linear value function approximation is that these updates form into this sort of very natural notion of how far off were you from the true value weighed by the features. Yeah.
Good question on the math here. So you have the gradient of w is equal to negative 1/2 alpha times the gradient, right? But you have a negative inside the v pi s minus v hat. So should it be a negative xs there with the negative 1/2 alpha on the left side as well?
You can push this into either, so the question is about just being careful about the negatives that come out. Yes, you could push that negative out into here. In general, alpha is a constant, so you can flip it and be positive or negative. Generally, you're going to want your, if you're minimizing this, it's going to be, you're going to be subtracting this from the weights, but you just want to be careful of depending on how you're defining your alpha to make sure that you're taking gradient steps in the right direction. Question. Okay, so how would we do this? Remembering again that we don't actually have access to the true value function, so we don't actually know. So in this equation, right, this assumes this is true. Like this is if the oracle has given you the value of a state under that policy, but of course we don't have access to that. So what we're going to do is sort of use the same types of ideas as what we saw in tabular learning, now with the value function approximation. So the return, which is the expected, or the return, which is the sum of rewards from time step t till the end of the episode, is an unbiased but noisy sample of the true expected return for the current state we're in on time step t. And so we can think about doing Monte Carlo value function approximation as really as if we're doing supervised learning on a set of state return pairs. So now what we're doing here is we're substituting in GT as an estimate of the true value. So we don't know what the true value is, but we know that the Monte Carlo return is an unbiased estimator, so we're going to substitute that in. Okay, so what does that mean if we're doing linear value function approximation? It means inside of our weight update, we have a G here. So we would take the state, we would take the sum of rewards on that episode. So again, this can only be applied in episodic settings, just like generally with Monte Carlo. And then we take the derivative, and in this case, that's just X. Our features, because we're using a linear value function approximation. And then on the last line, I'm just plugging in exactly what our v hat estimator is. So we're comparing our return to our current estimator, and then we're multiplying it by our features. And as usual, we have the problem that G might be a very noisy estimate of the return. Yes, and name first, please.
Do we differentiate first time and every time, like before?
Sorry, what?
Do we differentiate first time and every time visit, like before?
Great question. Do we distinguish between first time visit and every time visit? Yes. The same exact distinctions apply to Monte Carlo updating that applied before. So on here, I'm showing a first visit variant of it, but you could also do every visit. And it would have the same strengths and limitations as before. Every visit is biased, asymptotically it's consistent. Okay, so what does the weights look like in this case? We would say weight is equal to the old weights plus alpha times GT of S minus V hat of SW. Remembering that this is just X times W for that state times X of S. So it's very similar to what we saw before for Monte Carlo policy evaluation. What we do is we start off, in this case now, instead of having a value function, we just have a set of weights, which is going to now be the zero vector to start. Then we sample an episode. We have to sample all the way to the end of the episode using the policy. And then we step through that episode, and if it's the first visit to that state, then we compute the return from that state till the end of the episode, and then we update our weights. Yeah.
Just to check the math, are you adding the learning rate because of the negative in the gradient?
Just to check that, question is about the alpha, where, in terms of negative versus positive?
Right. I'm just wondering if you're making the gradient.
Yeah, so in general, this is going to look like this. I'm going to be a little bit loose on those. Alpha is going to be a learning rate that's a choice. Generally, we're going to be trying to minimize our objective function, or we're going to be reducing our weights. And we'll need to be a little bit careful about how we pick alpha over time. And this is being evaluated at each of the states that we encounter along the way.
And just to be careful, on step 6, do you need a gamma factor, or are you just adding up with no discount?
Good question. On step 6, was it? Oh, sorry. Said, do we need to have a gamma function? It's a good question. In episodic RL, you can always get away with gamma being 1. So if it's an episodic place, gamma can always equal 1. It is also fine to include gamma here. So here, generally in episodic cases, you will set a gamma being equal to 1, because one of the reasons why we set our gamma to be less than 1 is to make sure things are bounded in terms of their value function. But in the episodic case, it is always guaranteed to be bounded. But it is also completely fine to include a gamma here. Yeah.
So I kind of have a question about the same point, about this G. So when we do that, it seems like we will end up sampling G's that have rewards over episodes of different length, right? So doesn't that cause their distribution to be non-stationary and low variance?
The question is whether or not there's a problem with the fact that the returns you're taking are going to be sums over different lengths. It isn't. You're always trying to estimate the value of being in this state, which itself under this policy. And in the episodic case, you might encounter that state early on in the trajectory or late in the trajectory, and your value is exactly going to be averaged over whether you encountered it early or late and what are the returns. So there's no problem with, we're assuming all of your episodes are bounded. They have to be finite. So there has to be, with probability 1, your episode has to end. If that is true, then your rewards are always bounded, and then you can always just average over this, and that's fine. Sometimes you might encounter a state really early in the trajectory and have a lot of rewards. Other times you might encounter it at the end and have very few rewards, and the value of it is just the expectation of all of that. Yeah.
I want to ask for clarification. So essentially in this algorithm, you're updating the slope of the linear approximation every episode. So you start with an episode, you have a slope. then you take that slope and you update it given the following episode.
And not just once, so Tomas is and you're not just updating the weight once an episode, many times, right? So you look at all the states you encountered in that episode, and for each of those, you update your weight vector.
Which is equivalent of like generating all the episodes and trying to fit them in a single.
That so is like, well, what if we did this in a batch setting? So what if you generated all of your data and then afterwards tried to fit it? So this is an incremental approach to doing that, and they'll end up converging to the same thing. Good question. Yeah.
Just when you include gamma, should it be gamma to the power of j minus t so that you start discounting, like going forwards?
Yeah. Mm-hmm. Good catch. Again, you shouldn't need a gamma in this case. So in general, in this case, there should be probably, most of the time there'd be no gamma if you're in the episodic case, but it's good to be precise about these, so thanks. Okay. All right, so let's think about this for a particular example. It turns out that when we start to combine function approximation with making decisions and doing this sort of incremental update online, things can start to go bad. And what I mean by bad is that we may not converge, and we may not converge to places that we want to in terms of representing the optimal value function. So there's a nice example. When people were really starting to think a lot about function approximation in the early 1990s, Baird came up with this example where it can illustrate some of the challenges of doing function approximation when combining it with doing control and decision making. So we're going to introduce this example now with doing MC policy evaluation, and then we'll see it a few times throughout class. So what is this example showing? So in this example, there are going to be two actions. So A1 is going to be straight lines, and those are all going to deterministically go to what I'm going to call state S7. And this is state S1, S2, S3, S4, S5, S6. And what you can see inside of the bubbles there is what its feature value representation is. So remember I said that we would have a state and then we could write it down as a set of features. So what does S1 look like? It looks like 2, 2, 3, 4, 5, 6, 7. So weight 1 is 2 and weight 8 is 1. So what does S2 look like? S2 looks like 0, 2, 1, 2, 3, 4, 5. Go. S3 looks like this, and so on until we get to S7, which looks like this. Okay. So S7 looks a little bit different than the rest of them. That is the feature representation of those states. Now notice that it looks pretty similar to a tabular representation. In fact, there are more features than there are states. So there are only 7 states here, and there are 8 features. And that's completely possible, right? Like your feature representation could be larger than the number of true states in the world. So then we have action A1, and action A1 always takes us from any state deterministically to state S7. And then we have action A2, which is denoted by ... And what action A2 does is with probability 1/6, it takes you to state Si, where I is in 1 to 6. So basically, uniformly spreads you across one of the first 6 states. So there are only 2 actions. Either you deterministically go to state S7, or if you take the second action, then you go to one of the first 6 states with equal probability. And it's a pretty simple control problem because the reward's a 0. Everywhere, for all actions. So the value function for this is 0 because there's no rewards anywhere, and yet we can start to run into trouble in some cases. So before we get to that part, let's first just think about what like a Monte Carlo update would do. And let's just imagine also that there's some additional small probability here that from S7 that we actually go to a terminal state. So like let's say, with probability 0.999, we stay in S7, or like 0.99, we stay in S7, and 0.01, we terminate. And this is a slight modification, but I'm doing that just so we can do it for the Monte Carlo case. So we can think of episodes ending. So if you're in state 1 through 6, you can either go to S7 or you can stay in states 1 through 6. If you're in S7, you can either go to states 1 through 6, you can stay in S7, or you can terminate. All right, so what might an episode look like in this case? So let's imagine that we were in state S1, we took action A1, that deterministically gets us to state S7. Actually, before I do that, I'll specify we got 0 reward. Reward was 0, we went to S7, we took action A1, we got 0 reward, we stayed in S7, we took action A1, we got 0 reward, and then we terminate. That's our episode. Okay. So now we can think about what our Monte Carlo update would be. So our Monte Carlo update in this case would be, let's start with state S1 and try to do the Monte Carlo update. So for state S1, the return is what? 0. So the return is 0. What is x? Oh, and I should tell you. So let's start with initializing all of our weights to be 1. So what is our initial estimate of the value function of state S1? How many? So it's all of the weights are 1. The state S1 representation is 2, 0, 0, 0, 0, 1. 3, that's right. Okay. So, and that's just equal to our x times w. Okay. So then what does our update look like? And of course, I would have to tell you what alpha is. So let's say alpha is equal to 0.5. So what our weights are our change in the weights is going to be equal to 0.5 times 0 minus 3 times our feature vector for x. Our feature vector for x is 2, 0, 0, 0, 0, 1. So that means that we're going to get basically minus 1.5 times 2, 0, 0, 1 minus 3 times minus 1.5. So notice this is going to give us an update for every single weight, but it's only going to give us an update for the weights that are non-zero in this particular state, which is the first weight and weight 8. And so then if we were to actually get the new weights, so now we're going to have W is equal to W plus delta W, then our new representation would be minus 2, 1, 2, 3, 4, 5, 6, minus 0.5. So that would be one update of Monte Carlo for the first state. Now, you would do this for every single state in that episode. So you would then do it for the first time you see it in the algorithm I've defined before. So we would next do this for state S7 as well, where the return would also be 0, but the value would be something different. So we would get a different, well, actually in this particular case, the value is also 3. It depends, if you've already updated your W, then your value will already be different. Yeah.
So we're doing SGD per state, not per episode.
Right. The question is, are we doing SGD per episode or state? We do it per state. Yeah.
In the previous slide, when you had the for every state, that every encounter, does that mean that
for every first visit in that episode?
So yes,
yeah.
And it's within that specific episode. So when you go to a new episode, that would reset.
The question is about sort of this first visit. We basically step along that episode similar to what we did with Monte Carlo before. And the first time we encounter a state in that episode, we update the weights using its return. And we do that for every single unique state in that episode the first time we see it. And then after all of that, we get a new episode. All right, so this is what would happen. And you can see that the changes can be fairly large because we're comparing like the full return to our value function. Depends, of course, on what our alpha is, and alpha can change over time. Generally, we'll want alpha to change over time in order to get convergence. But this gives an example of sort of what Monte Carlo updating would look like in this case with linear value function approximated. Okay, so a natural question might be, does this do anything reasonable? Are we guaranteed that this is going to converge to the right thing? And what does the right thing mean here? We're constrained by our linear value function approximator. So we're going to say, are we going to converge to sort of like the best thing in our linear value function approximator? Okay. Before we do this, let's just talk for a second about the distribution of states and how that influences the result. So if you think back from maybe the first or second lecture, we talked about the relationship between Markov processes, Markov reward processes, and Markov decision processes. And we said that once you define a particular policy, then your Markov decision process is actually a Markov reward process, where you can think of it as a chain where the next state is determined by your dynamics model, where you only use the action according to your policy. So if you run that, if you run your sort of Markov chain defined by an MDP with a particular policy, you will eventually converge to a probability distribution over states. And that distribution over states is called the stationary distribution. It's a probability distribution. It's saying sort of like what percentage of the time are you going to be in state 1 on average versus state 2, et cetera. It has to sum to 1 because it's a probability distribution. You always have to be in some state. And it satisfies a balance equation. So it says that the probability distribution over states before summed, yeah, I guess, let me just flip this. I think it's a little bit easier to think about it the other way around. Okay. We've got d of s prime is equal to sum over s, sum over a. We're just doing the sum over a right now so that we can be sure that we allow ourselves to have stochastic policies. So we look at all the actions that we could take under the current state, and then we look at where we could transition to on the next state. So we are in some distribution over states. We think of all the actions we could take from each of those states, where we might transition to, and then that gives us a new distribution over states S prime. And those two have to be identical. So this is often also thought about in terms of a mixing property. When your Markov chain has run for long enough, this balance equation will eventually hold. And this is just that your distribution over states on the previous time step has to be exactly the same as your distribution over states on the next time step after this process is fully mixed. And it's just telling you on average, how much time are you spending in what's the probability on any particular time step you're going to be in a particular state. This is not telling us how long it takes for this process to occur. So this depends a lot on the underlying dynamics of the system. So it might be that this takes millions of steps until you reach the stationary distribution, or it might mix pretty quickly. It depends on the properties of your transition matrix under the policy. We're not going to get into any of that in this class. It's just important to know that you can't, it's not like you can just wait 100 steps and definitely you're going to be in the stationary distribution. It depends on the problem. Yeah. And remind me your name. Yeah.
Have there been any proven bounds in the mixing time of these Monte Carlo methods?
About whether there's any proven bounds on the mixing time of these type of Monte Carlo methods. Not that I know of. There might be some. It's a really tricky issue often because you don't know how long it will take to get to this sort of stationary distribution. There's a really cool paper that just came out like a month ago at NeurIPS that talks about how when we're thinking about off-policy evaluation, which we'll talk more about later today, instead of thinking about sort of per step ratios or whether you'll take a certain action in a certain policy or not, you can think about these stationary distributions and the difference between them in different policies. The problem is you often don't know how long and whether your data has got to that stationary distribution. So it would also be really nice if there were easy tests to tell if this was true. That's also really hard to know. Yeah.
Sorry, returning to the Baird 1995 example.
Yes.
Could you why does it converge or what you were saying then?
Yes, so the question is about Baird. So I sort of gave a long, Tony's, you gave a long prelude about saying like that things might not converge, but everything looked fine there. Are we going to go into that more? Yes, and we're going to talk about the fact that actually in the on-policy setting, when we're just doing policy evaluation, everything's going to be fine. It's only when we get into the control case where we're going to be using data from one policy to estimate the value of another, where in this example and many others, things start to go awry. So we'll use this as a running example, but right now there's no reason for you to believe this is pathological. Okay, so this is the stationary distribution, and then the convergence guarantees are related to that. Okay, so what we're going to do is define the mean squared error of our linear value function approximator with respect to the stationary distribution. Why is this reasonable? Well, because you probably care more about your function approximated in error in states that you visit a lot. If there's a state that's really, really rare, probably it's okay to have bigger error there. You want your overall mean squared error to be defined on that stationary distribution. So this is the mean squared sort of value prediction error, and it compares what we predict versus the true value weighed by this distribution of states. And what we're assuming for right now is that the approximation we're using is a linear value function approximator. Let me just note for historical reasons that John is at Sitclis and Ben Van Roy. John is at MIT, and I had the pleasure of him teaching me probability, which was great. And then Ben Van Roy is here and was one of, I think, John's PhD students or postdocs. Anyway, they, in about 1997, people were getting really interested in whether or not when you combine function approximation with reinforcement learning, what happened and whether things were good or bad, and they're responsible for this nice analysis. So let's assume we have a linear value function approximator. What you can prove is that if you do Monte Carlo policy evaluation, linear value function approximators, you're going to converge to the weights which have the minimum mean squared error possible. It's kind of the best you could hope for. So this is saying in the limit is you have lots and lots of data, and you run this many, many, many times, then you're going to just converge to the best weights possible. Now this error might not be zero because it might be that your value function is not approximatable with your linear set of weights, but it's going to do the best job it can. So it's just going to find the best. It's basically just doing the best linear regression that you can do, okay, on your data. So that's good. That's sort of a nice sanity check. It's going to converge to the best thing that you could hope to do. Some people have been asking about, okay, well, I'm giving you this sort of incremental method. And maybe in some cases that's reasonable. Maybe you're running like a customer recommendation system and you're getting data over time and you're updating this estimator. But in some cases, you might have access to just a whole bunch of data from this policy. And couldn't you just do that kind of more directly? And the answer is yes. So this is often called batch, Monte Carlo value function approximator. And the idea is that you have a whole bunch of episodes from a policy. And the nice thing is now you can just kind of analytically solve for the best approximator. So again, our GIs are going to be our unbiased sample of the true expected return. And what you can do is now N is just our set of data. This is really a linear regression problem. We're going to use our unbiased samples as estimates of the true value function. We're just going to find the weights that minimize this mean squared error. You take the derivative, you set it to 0. It's linear regression. You can solve for this analytically. So a little, just like how we talked about, you could do policy evaluation analytically in some cases. You can also do it analytically in this case for the linear value function approximator. And note again, this is Monte Carlo. We're not making any Markov assumptions. We're just using the full return. So this is also fine in non-Markov environments.
Can you speak to the advantages of this approach versus our iterative method that we used with the linear value approximation for policy evaluation?
Yes. Asking about, okay, so when we'd want to do this versus the other iterative one, this generally has higher computational cost. X can be a very large matrix. It may not be possible to even write down X. X is all of your data in the feature representation form, and it requires taking a matrix inverse. So that may not be feasible if you've got huge feature vectors and millions or billions of customers. Facebook can't do this and do this directly. And also, if you're doing this, you could do this sort of incrementally, but you're always refitting with all of your data. That also could be very expensive. So most of it's about memory and computation. If you have a really small case, it's probably a good thing to do. And it also depends whether you already have all your data or not. Yeah.
You could also do sub-batch as well, right? And that could help with convergence and not having your gradient estimations fluctuate quite as much.
Absolutely. So as of course, there's an in-between. So you don't have to, if you have access to quite a bit of data, you could either do it completely incrementally or all batch, or you could do sub-batches. And there's some nice work by my colleagues and also us showing that in terms of, we get into deep learning, there can be a lot of benefits to doing sort of some amount of this analytical aspect over like, a sub-batch of data, because you're sort of, particularly when we get into TD learning, you're kind of propagating information a lot more quickly than you are if you're just doing this sort of incremental slow update. Because remember, in TD learning, we're also kind of only doing like one step of backup compared to kind of propagating all of our information back like we do with Monte Carlo. Okay. All right. So now we're going to get into temporal difference learning. So remember, in temporal difference learning, we're going to use both bootstrapping and sampling. Monte Carlo only uses sampling to approximate the expectation. TD learning also uses bootstrapping because we don't have to wait till the end of an episode. We just bootstrap and combine in our estimate of the expected discounted sum of returns by using our current value function. So in this case, what we used to do is we would bootstrap. This is the bootstrapping part. And what we often call our target is the reward plus gamma times the value of the next state. And I remember the reason this is sampling is we're sampling this to approximate our expectation. We're not taking the full probability of S prime given SA and summing over all of S prime. So before we did this and we represented everything as a table, now we want to not do that anymore. So let me just, before we get into this, let me just remind us the three forms of, or the forms of approximation we're going to have now. Now we're going to have a function approximation, bootstrapping, and sampling. But we're still on policy. What do I mean by that? Right now, we're still just doing policy evaluation, which means we're getting data from the policy that we're trying to estimate its value. It turns out things are just way easier in that case when you're on policy, and perhaps this should be somewhat intuitive. It's quite similar to the supervised learning case. Supervised learning, you're generally assuming your data is all IID. Our data is a little bit more complicated than that, but our data is closer to that in this case because we have a single policy. It's not sort of this non-stationary aspect that comes up when we start changing the policy. So right now we have these three forms of approximation: function approximation, bootstrapping, sampling, but we're still on policy and mostly things are still going to be okay in terms of convergence. So what does that look like? We're again going to sort of think about doing the equivalent of supervised learning. We'd like to just have our states and the oracle tell us what the value is and fit our function. Instead of having the oracle, we're going to use our TD estimates. So we're going to use our reward plus gamma times our approximate value of the next state. And that's going to form our estimate of what the true value is. Okay? And then we're going to find the weights to minimize the mean squared error in that setting. So if we do that, what we can see is that if we're doing the sort of the linear case, we write this out as just, this is the TD target. Just as a quick side note, I'm going to use the word TD0 a lot. We haven't talked about it in this class, but there's actually a whole bunch of different slight variants of TD, which are often called TD gamma. And so if you're reading the book, that might be a little bit confusing. So I just want to be clear that we're doing the TD0 variant, which is probably the most popular. There's a lot of other extensions. For simplicity, we're just going to focus on TD0 for now. So this is the TD target. This is our current estimate, and then we take the derivative. In this case, that means that we're going to end up plugging in our linear value function approximator for both our current state, the next state, and looking at that difference weighed by the feature vector. So it should look almost identical to the Monte Carlo update, except for the fact that now we're bootstrapping. So instead of this being G versus being the G return of that we saw before for a particular episode, now we're bootstrapping and we're getting the immediate reward plus an estimate of the discounted sum of rewards, which we're using our value function approximator to estimate. So this is what the TD learning linear value function approximation for policy evaluation algorithm looks like. Again, we're going to initialize our weight vector. We're going to sample a tuple, and then we're going to update our weights. So we get to now update our weights after every single tuple, just like what we saw for TD learning. And what we can see here is that we're just plugging in our particular estimator minus our old estimator times x. So let's see what this looks like on the Baird example. So again, we have the same state feature representation as before. State 1 is 2, 0, 0, 0, 0, 0, 1. We still have 0 rewards for everywhere. Let's set our alpha equal to 0.5. Now we're in the case where we can say that there is no terminal state because TD learning can handle just continuous online learning. So we're just going to assume that S7 always stays in S7 under action A1. So A1 is the solid line and A2 is the dashed. And we're again going to initialize our weights to 1, 1, 1, 1. And then let's look at this tuple. So just like the first tuple we saw before, let's imagine we're in state 1, we took action A1, we got a reward of 0, and we went to state S7. So why don't we take a minute and you calculate what the new weights would be after we do that update and maybe compare back to the Monte Carlo case in terms of how much they have changed. And feel free to talk to a neighbor. I'll just make this a little bit bigger so it's easy to remember what S7 is. All right, have they moved a lot, a little? How much have the weights changed compared to what we saw with Monte Carlo? Seen some people indicate smaller. Yes, that's right. Okay, so the initial value of the states, this is going to be, so for x of S1 times W, it's still going to be 3. For x S prime is 7. If we look up what that is, this is also going to be 3. Okay. But now what we're going to have is we're going to have delta W is equal to alpha times 0 plus 0.9 times 3 minus 3. Okay, so that's going to be equal to alpha times minus 0.3. So remember before it was actually minus 3, so it was a much bigger update. And so then when we add that into our new weights, we're going to move our weights, but we're going to move them much smaller than we saw before. And this shouldn't be too surprising. It's sort of consistent with what we saw for Monte Carlo updating and TD learning. TD learning is only updating these sort of smaller local changes, like one state action or word next state. The Monte Carlo is saying this is an full episodic return. It's not bootstrapping. So it's saying, no, really, the return from starting in state S1 is 0. So we're going to move it a lot more. Here it's saying, okay, I'm going to pretend that the return from state S1 is 2.7, which is close to 3. It's not 0. So when we move our weights over here, the difference is going to be much smaller than what we saw for Monte Carlo, which is similar to what we saw without function approximator. All right, what are our theoretical properties in this case? Pretty good. So these are also, if you look at TD0, you're going to converge to weights, which aren't necessarily quite as good as Monte Carlo, but they're within a constant factor. So they're going to be 1 over 1 minus gamma of the minimum possible. So they're not quite as good as Monte Carlo, but they're pretty good. And depending on your discount factor and the function approximator possible, this varies in terms of benefits. So just to check our understanding for a second, I've put up both of these results. So one says the Monte Carlo policy evaluator converges to the minimum mean squared error 1 possible under your linear value function approximator, and TD0 converges to within 1 over 1 minus gamma of this minimum error. So again, what is this minimum error? This says if you could pick any linear value function approximator, how good could that be at representing your true value of your policy? So let's take just another minute, and this is a good one to talk to a neighbor about. If the value function approximator is the tabular representation, what is the MSPE for both Monte Carlo and TD? Can we guarantee to converge to the optimal solution, optimal value for the true value for V of pi or not? And if it's not clear what the question is, feel free to ask.
So when you say it's a tabular representation, do you mean that you're reducing the representational capacity of the system? Or
Question is, if I say it's a tabular representation, what do I mean by that? I mean that there's one feature for each state. It's like a one-hot encoding. So it's like the same representations we saw for the first few lectures, where like for each state, you have a table lookup for that value of that state. Yeah.
Can you just
And my
explain?
name first.
Can you just explain what the zero means in TD? Like, is there a difference between TD and TD zero?
Good question. So TD0, everything we're seeing in question is about TD versus TD0. Everything we're talking about in class right now is TD0. I'm using that because there are multiple versions of TD, and if you look at the book, they'll have TD lambda sometimes too. So I'm just making sure it's clear. So if you read other resources, you'll know which version of TD to map to. All right. Well, first question for the if we're using a tabular representation, can we exactly represent the value of a policy? Well, if we're using for every single state in the world, you can have a different table at representation. Can we exactly represent the value of the policy? Yes. Yeah, we can. So if you have one feature for every single state in the world, it's not going to be practical. We can't actually do this, but you can exactly represent the value of a policy. How could you do this? You could simply run the policy for every single state, do Monte Carlo returns and average, and that would give you the true value of the state. So you could do it. You could represent the expected discounted sum of returns by representing that in every single table. So that means that this error is equal to 0 because your functional capacity is sufficient to represent the value.
On that, so that what we're saying is in expectation, right? The difference between what your function predicts and what it actually is 0. But in each episode, it may be different.
The question is, in expectation, it's 0, but in any episode, it's different. In this case, if you have a tabular representation, and this is in the limit, so with infinite amounts of data, et cetera, then this will be 0 for every single state. So this will equal 0 for every state. You will converge to the right value for every single state if you're using a tabular representation. And that's because if you think of just having like literally infinite amount of data and you run your policy just, infinite amount of times, then for every state you have an infinite number of trajectories starting from that state, and you can write down that value separately in a table. So it'll be 0. So what that means is that the mean squared value error for the Monte Carlo estimator is 0 if you're using a tabular representation. And because it's 0, that is exactly the same as the mean squared value estimator for TD, except for, so this is just equal to MSVE of the Monte Carlo times 1 over 1 minus gamma. So that means that this is also 0. So if it's a tabular representation, just to sort of connect back to that, none of these methods have any error. Yeah, question in the back. And name first.
Me?
Yeah.
I'm wondering where the 1 over 1 minus gamma constant comes from.
Yeah, so the question is, where does that 1 over 1 minus gamma constant come from? In the interest of time, I'm not going to go through it too much. I encourage you to read the Tzitz-Siklas paper. Intuitively, there is error that's propagating here because of the fact that we're bootstrapping. And so if you have a function, what this result is sort of trying to highlight is that if your function approximator actually has no error, then there's going to be no difference between Monte Carlo and TD. Because for both of them, the mean squared value error inside of that sum, the minimum over W, is going to be 0. So it doesn't matter whether you're using TD or Monte Carlo. But if that's not true, like if you can't actually exactly represent the value function, then you're going to get error. And that error is going to, basically you can think of 1 over 1 minus gamma as approximately the horizon H. And basically that's getting multiplied because you're adding up these errors. And the reason those get added up is because you're bootstrapping. So you're propagating that error back, whereas Monte Carlo doesn't suffer that. Yeah.
In general, the mean squared error is taken over a distribution of the states, but
under the policy, yeah.
Yeah. Under a specific policy, but the only specific one we've seen is a stationary distribution.
Yep.
Do you ever use another one?
Great question. Okay, right now we're seeing this under the stationary distribution of the states that you're going to reach under the policy that you care about evaluating. For that, I think that's the right choice because that really is the states you're going to get to under this policy. When we start to think about control, you might want others, like if you're going to change your policy. Okay. All right, so let's, I guess, just briefly more on this. Are they faster? Is one of them better? To my knowledge, that's not really understood. If you come across any literature on that, I'd love to hear it. Practically, TD often is better. Just empirically, often the bootstrapping often helps you a lot. All right, let's move on briefly to control. It's going to be pretty similar. So instead of representing the value function, we're going to represent the state action value function, which is what we saw before when we wanted to often move from policy evaluation to control. And now what we're going to do is we're going to interleave sort of policy evaluation with a value function approximator with performing like an E-greedy policy improvement. This is where things can start to get unstable. What are we doing in this case? We're generally involving function approximation, bootstrapping. We're often are also doing sampling. But really, the really big issue seems to be the off-policy learning. But when we think about before we had this nice stationary distribution or we're converging to a stationary distribution over states, we're not going to be doing that anymore because we're going to be changing our control policy over time. And so that's changing the distributions of states that we encounter. And Sutton and Bardo often call it the deadly triad. They say once you start combining function approximation and bootstrapping and off-policy learning, things start to get a little bit, they can fail to converge or converge to something good. All right, but before we get into that, let's think about it procedurally. So now we're going to have Q functions that are parameterized by a W, and we can again do stochastic gradient descent. This is going to look almost identical to what we had before. And again, the stochastic gradient descent can sample the gradient, which means for a particular state action pair, then we're going to do these updates. So here what we're going to do is we're going to represent our Q function by a set of linear state action weights. So that means we're going to have features that sort of both encode the state and the action. So like what I saw when I was turning left as my robot, for example. So it's going to be a combination of these two. And then once we have that, then we're going to just have a weight vector on top of that for the Q. So we're not having separate weight vectors for each action. Instead, we're having features that try to encompass both the state and action themselves. And then we can do our stochastic gradient descent on top of that. So how does this work for like Monte Carlo? It's going to look almost identical to before. We're just going to, again, use our return. Now we're going to be defining returns from a particular state action. If we're doing first visit, the first time we reach the state action in that episode, we look at the return, the sum of rewards till the end of the episode, and we use that as our target. Use that as our estimate of the oracle, the true Q function, and we update towards that. In Sarsa, we're going to use a TD target. So we're going to look at the immediate reward of our tuple plus gamma times Q of the next state that we encountered and the action we took. And so then we're again going to just plug that in. And then for Q learning, it's going to look almost identical to Q learning, except for, again, we're going to plug in function approximators everywhere. So we're going to plug in this, remember, is going to be a function of Rx, which is going to be a function of S prime and A prime times RW. Whereas here, this is going to be a function of the state in action. Everything's linear, and we're just doing different forms of bootstrapping and comparing whether or not we take a max or not. All right, so I went through that a little bit fast, but it's basically exactly analogous to the first part, which we sort of stepped through more carefully, except for everything's with Q functions now. Why might this get sort of weird or tricky? So TD with value function approximation is not really following a gradient. I don't have time to go into a ton of details on that today, but there's some nice explanations on this in chapter 11. So Sutton and Bardo, chapter 11. It's a great resource. And we also have lecture notes available online. And so informally, we're sort of doing this interleaving of doing this like approximate sampled Bellman backup combined with what's often known as a projection step because we're trying to sort of project our value function back into the space of representable functions. And intuitively, for why this might start to be a problem is that the Bellman operator we showed is a contraction. Like when we're doing dynamic programming, we showed that if you do Bellman backups, you're guaranteed to converge to a fixed point. When you do the value function approximator, it can be an expansion. What does an expansion mean? Well, what a contraction, just as a reminder, what a contraction said is, let's say for an operator that's a contraction, if you apply this operator, and this is an operator like the Bellman equation, Bellman backup, if you apply it to two different value functions, the distance between this could be like a max norm or something like that, is less than or equal to the previous distance. Which means as you apply this operator, the distance between your old value function and your new value function keeps getting smaller and smaller and smaller, and eventually you get to a fixed point. The problem is now we're not doing that anymore. It's more like we're doing like OV, and then we do some sort of projection operator. I'm just going to call it kind of a weird P. So this is the projection operator. It means when you compute your new value function, it may no longer lie in your value function approximator space. You're going to have to refit it back into that space. And when you do that, that operator itself can be an expansion. For those of you that are interested in some of the early sort of discussions of this, Jeff Gordon has a really nice paper on averagers from 1995. Where they talk about how linear value function approximators can be an expansion. So the Bellman backup is fine, it's a contraction, but when you do this approximation, you might expand the distance, and that's one of the problems. Okay, so if we go back to our Baird example and think about this a little bit more in terms of the control case. So let's imagine that we have a setting where you have two different policies. And the first policy, and this is the policy that you want to evaluate, you always take the solid line. So you always take A1. And in your behavior data, this is the data that this is the policy you're using to gather data. You take A2 with 6/7 of the time, and you take A1 1/7 of the time. Gamma is 0.99. And what you do is you generate a whole bunch of data. So you generate data under your behavior policy. So there's some really cool work on how you deal with sort of correcting for the data that you're getting versus the data you want to evaluate. Let's imagine we don't go into any of that, which I think is super cool, and instead we're just going to do something super simple, which is we're going to throw out all the data that doesn't match. So imagine you just throw away data if A is not equal to pi of S. So you generated all these data points. So what do I mean by data points here? We had S, A, R, S prime. So you take all these tuples. If it turns out that the action that was taken there is not the same as the policy you want to evaluate, that where you're only ever taking A1, you just throw out that tuple. You don't update. So now all of your remaining data is consistent with your policy. So let's imagine then you tried to do TD learning with that data. The problem is you can diverge. And what do I mean by that? It means that your weights can blow up. Super interesting why this happens. The main intuition for it is that your distribution data is not the same as the data that you'd get under your desired target policy. In particular, if you were actually to run the policy you care about, pi, what would happen? Let's say you start off in state S1, you take A1, that deterministically gets you to state S7. Then you're going to stay in S7 for a really long time because it's deterministic. So you get like S1, S7, O7. Let's say even you did this, maybe it was an episodic case and you have multiple episodes. You'd still have cases where you'd like have very little amount of data about these S's and lots of data about S7. But in the data that you get from your behavior policy, because a bunch of the time it takes A2, it'll keep teleporting you back to one of S1 through S6. Which means the distribution of the data you have looks very different. The distribution of states you visit looks very different than the data that you get from the states you'd visit under pi. And that is the problem. If you don't account for this mismatch, then the values can diverge. Even though they're all sort of compatible, all in the sense that you're only ever using a state action pair if you took the action under your desired policy. And this sort of issue can also come up when you're using Q-learning and you're doing generally like updating this policy over time. So in terms of this, just to briefly summarize before we finish, in the tabular case, everything converges. It's beautiful. In the linear case, what I mean by this, I mean that can chatter. You basically converge, but you might there might be some oscillation. But Q-learning, like where you're doing this off-policy aspect, can diverge. And once we get into nonlinear value function approximation, like mostly all bets are off. Now, this is a little bit of an oversimplification. There has been a huge amount of work and huge amount of interest in this because everyone wants to do function approximation with RL so we can tackle real problems. And so over the last like 1 or 2 decades, there's been a huge amount of work on this. And there are some algorithms now that do have convergence guarantees. And there's some super cool, really recent work where they're looking at batch RL, which can converge with nonlinear approximators. So there's definitely a lot of work on this that we're not going to get to. I just want to highlight that it's a really important issue, not just whether it converges, but what it converges to. Like you might converge to a point, which is a really bad approximator. So it's stable. It doesn't, your weights aren't blowing up, but it's just a really bad approximator. And some of the critical choices here are your objective function and your feature representation. So just before we close, I think this is a really nice figure from Sutton and Bartow. What they're showing here is you can think of it as like you have this plane, which is where you can represent all of your linear value function approximators. And what happens when you do a Bellman update or like you do a TD backup is that you're going to now sort of have a value function that might not be representable in your plane. Then you can project it back. And these you can quantify different forms of error. Basically this allows you to find different objective functions that you're trying to minimize in order to find the best approximator. And we've seen one today, which is sort of this minimum mean squared error approximator, essentially over these Bellman errors, but that's not the only choice, and it's not necessarily even the best choice, because it might be that the one that has the smallest error there is not the same one that has the best performance in your real problem. So that's a little bit fast, but it's super interesting. It's covered in Sutton and Bartow in 11 if you want to go into more detail. Just really quick, what are the things you should understand? You should be able to implement these ones on linear value function approximator, both for policy evaluation and control. You should understand whether or not things converge in the policy evaluation case, and when the solution has zero error and non-zero error. And you should just understand qualitatively what are the issues that can come up so that some of these solutions may not always converge. And it's this combination of function approximation, bootstrapping, and off-policy learning. All right, so that's enough to sort of get started with the homework 2 that we're going to be releasing this today. And then next week, we're going to start to talk about deep learning. Thanks.